And first of all, I would like to acknowledge all the co-authors who made a great contribution to the presentation. And dual energy CT is not a new concept. As a matter of fact, not long after the invention of CT, people proposed the dual energy concept. So dual energy, if you look at it, basically take advantage of two fundamental interactions of X-ray with matters. One is a photoelectric effect, one is a Compton effect. So if we look at the mass attenuation coefficient of any material, it can have two components. One is contribution from the photoelectric, one is Compton, as shown by this equation over here. And then if you follow through the derivations and so forth, you can show that the mass attenuation coefficient of any material can be a linear combination of two other materials. That means you can arbitrarily select two materials which uses as a basis material, and then to express the mass attenuation coefficient of the third one. And also, if you look at the photoelectric and Compton effect, typically at the lower energies, you have predominantly photoelectric effect, and then at the higher energies, you have a Compton effect. This is one reason why in the data collection process, you typically collect at the low KVP range, and then you collect another data set at a high KVP range. So if we look at the concept of using two materials to represent the mass attenuation coefficient of third looks pretty strange. But if we take a closer look at this graph shows three materials which typically appear in the human body: iodine, bone, and soft tissue. And if you look at if we want to express the yellow curve, which is a bone, by the attenuation coefficient of the blue curve, which is iodine, and the pink curve, which is soft tissue, they don't look similar at all. But if we ignore the low X-ray energy range, that means all the X-ray above the K-edge of iodine, you can see that the three curves are pretty much similar. As a matter of fact, you can show that mathematically you can use this kind of best fit to use water and iodine to map out the bone attenuation coefficient. So this is an intuitive explanation of why you can use two materials to represent the third. So here is an example of how that is being done. So you collect, this is a chest phantom. In the center, it's a stationary phantom with a heart filled with iodine. You collect with 80 and 140 kVp scans, and then you're doing a nonlinear map, and the fourth speaker will talk about all the mathematics and the reconstruction process going through that. And then you can map into two density projections. One is a water density, one is iodine density. Of course, you can map to two other materials as well. For this example, we happen to pick water and iodine. There's a couple characteristics you will notice that in the water density images, there's no appearance of iodine. All the iodines has been removed. And also similarly for the iodine density images, all the soft tissue portion has been eliminated as well. Also for the third material, which is neither iodine nor water, you can see that they have contributions in both. For example, the bone. They have contributions to both water and iodine. And another thing we should emphasize is once we have done this, the images on the right is no longer represented by the Hounsfield unit. It is pure density measured in gram per cc. So if we carry this further, since we can always represent the mass attenuation coefficient of a third material by the two basis materials, you can show that if we look at the projection measurement, which is a line integral of attenuation coefficient, at a specific energy can be expressed as a linear combination of the two density projections. The line integral here represents the density projections of two basis material, A and B. In the previous example, will be water and iodine. So therefore, if we fixed at a particular energy, since we know what the mass attenuation coefficient of water and iodine is, because we can just go to the website of and download all the coefficient. So we basically can generate or synthesize a set of monochromatic projections. This is a projection of line integral of a specific energy collected along a path. Therefore, if you look at the X-ray CT, typically the X-ray photon come out of the scanner has a very broad spectrums. This is an attempt where we can try to mimic or simulate a set of projections as if the X-ray source have a monoenergetic X-ray coming out. So here is an illustration where you start with 80 and 140 kVp, and you convert that projection set into two material bases and use this equation to convert into monochromatic energy images. Of course, by selecting different E0 values, you can generate all different energies ranging all the way from very low to very high. So the question is, how do you select the best energy to represent? So typically, there is an optimal point where you want to set your monoenergetic X-ray beams. At a lower keV, your contrast is high, but your noise is also high. And also for high keV, your contrast reduces. There is an optimum point where, based on the mathematics, that because you're weighting two random samples, there's a point where you achieve the best noise, and also you haven't sacrificed too much about the low contrast detectability. So typically for every examinations and so forth, there's an optimum range of keV where you want to set your monoenergetic projections. Typical ranges is between 70 to 80 keV. So now we have discussed all the fundamentals or basics about dual energy imaging and monochromatic imaging generation process. Now, how do we collect the two energies, 80 kVp and 140 kVp? There are various approaches, as Bruce mentioned before, and the approach taken by GE is using fast kV switching, where in the first projection view, you collect 140 kVp, and then you quickly switch both the generator and X-ray tube, so it generate 80 kV images, and then for the next view, again, you switch again. So in this process, typically, if you look at the CT data collection, it collects roughly 1,000 projections over 360-degree views in a fraction of a second. In order to achieve this, we actually more than double the amount of sampling frequency because we want to support all the necessary sampling criteria. So in this case, the time interval between high and low kVps is a small fraction of a millisecond. So to achieve that, there's a lot of technical challenges. And definitely you need a very high powered X-ray tube. You also need a very low impedance generator, low capacitances generator to make sure you are switching the through rate is very high. Also, you want a very high sampling rate of DAS that can sample very fast at a very low electronic noise floor. And of course, you need a very fast scintillator. So we're going to talk about a little bit about the scintillator itself, why the scintillator is important. So scintillator is a solid state material, typically has the characteristics that if you bombard the scintillator with X-ray photons, if you shut off the X-ray photons, the signal doesn't go to zero right away. There's a gradual decay, similar to the phenomena where you sit in a dark room watching the old style CRT tube. When you flip the remote control, the TV screen doesn't go blank right away. It gradually dies off. And similarly here, so if you look at the typical afterglow or primary speed decay curves, this is one of the popular scintillators people use. You can see that there's a slow decay. Because of slow decay, although you can switch on the generator and the tube side very quickly, but still there's still signal contamination from the high signal to the low signal and vice versa. So you really want to create a scintillator that can switch very fast. So Gemstone was a scintillator that under development for 9 years, try to find the best material that can achieve these purposes. So the red curve on this graph shows the response of the Gemstone. You can see that the primary speed is very fast. The response is nearly instantaneous. Another thing is for the scintillator, you have to make sure that it's stable. That means it doesn't change its behavior because of environmental changes. This scintillator, to expose to a very extreme conditions where we'll put a scintillator under the boiling water, boil for quite a while, and the response of the scintillator doesn't change. So it's a very stable material. In addition, this material can be force molded. So you can mold to any shape you like. And the Detector engineering actually molded one monkey shape, as over here. I guess they have too much time on their hand. So for the data collection, how the data is collected. So if you, most people are familiar with a sinogram. Basically, you collect one view at a time. So you collect a low view and high signal and so forth, alternately build up one complete sinogram. And then you can split this sinogram into the low KVP portion, and then you also can split into high KVP portion. So these are basically your conventional 80 KVP and 140 KVP projection data set. Of course, from that, you can generate the conventional images where you can use for QC or quality control purposes. Based on what we discussed previously, you can use a nonlinear mapping process to map this set of sinograms into two density projection sinograms. In this case, it's a water and iodine. And based on these two sinograms, using reconstruction algorithms, you can generate the iodine density equivalent density images and water equivalent density images. And from this, based on the previous discussion, you can map into monochromatic images. So from this graph, I hope you'll get the impression that previously, for a CT scan, after one scan, you generate one set of images. Now, this is no longer the case. You suddenly got a variety of different images, and here we only show you one material pairs. You have many, many different material pairs depend on the clinical application on hand. Also, for these monochromatic images, you have many different energy levels you can generate. So we are no longer just simply generate an anatomical information, but now you start getting into the material characteristic portion of the study. So what is the advantage of dual energy CT? Here is an illustration of a phantom study. This is a patient kidney scan where the phantom here is try to mimic what the kidney is. Typically, in the conventional CT, there is a dependency of amount of contrast present and the CT number variation depend on amount of contrast present in the kidney due to beam hardening effect. So if you measure with a conventional CT, the CT numbers for different regions, you can see that it varies significantly. So if we want to separate between the malignant and benign or cyst versus mass type of lesions, you can see that it is very difficult because their CT numbers overlap. However, with a monochromatic image generation process, because in the projection space based projection processing process, you eventually remove the beam hardening effect. Therefore, your reconstruct values are very stable, independent of the location and its surrounding materials. Here is a typical illustration of the beam hardening effect that seen in a posterior fossa region of a human scan. And this type of artifact has been with CT since day one. And that's a dark streaking connecting between two petrous bones. And with the dual energy applications, you can successfully remove that beam hardening effect with monochromatic image generation process. So what other applications can be used for dual energy? One of the applications in CT is try to differentiate between different tumors. Some are malignant, some are benign. But sometimes with single energy CT, you cannot differentiate them. As illustrated in this picture over here, this is a patient where there are two different lesions. And both lesions shows hypo-enhanced. That means there is some iodine contrast take up activities. So, which one is a malignant, which one is a benign? CT typically cannot answer that. So historically, we always send the patient to MR for further diagnosis. And this is a study done by Mayo Clinic, Dr. Hara. And basically, he used dual energy CT and then look at using a water and iodine as a material basis. If you look at in this graph over here, the water-based image for the malignant tumor, you can see that the density of that is very similar to the surrounding tissues. This is an indication that the tumor is highly vascularized. That means it's the probability or the potential being malignant is high. On the other hand, if you look at for the cyst, which is a benign tumor, you can see that for the iodine portion of the image, the density is significantly equal to the background. That means very dark, so indicating there's a very little uptake in the contrast enhancement. So if you measure the CT numbers in all the regions, you feel plotted as a function of a water-based density and versus iodine-based density. You can see that those two are grouped separately. Of course, if you only look at the water density images, there's a significant overlap. If you only look at iodine density images, there's also a significant overlap. But if you project this onto the angle, you can see that those two groups are well separated. Another example which I want to illustrate here, also example provided by Mayo Clinic, is this case over here. For this particular tumor, you can see that there's a bright spot. The question is this iodine enhancement or is this something else? If it's enhancement, it's indicating some malignancy. But if it's something else, maybe it's not a malignant tumor. So with a dual energy approach, with a water and iodine separation, you can see that because we know in the water-iodine pair images, the water density, equivalent density images have no contribution of iodine. So this one definitely is not a contribution of iodine. It is a contribution of calcium. So it is not lucky for the patient. Similarly, for these examples, if you look at the kidney, there's a kidney stone buried in this kidney exams. And but if you just look at the low KVP or high KVP images, you can't tell where the kidney stone is or if there's a kidney stone present. But if you look at the water-iodine pairs, you can clearly identify in the water density images the presence of the kidney stone. Of course, use a dual energy, you can not only identify the kidney, but also classify different kidney stones. Because for different type of kidney stones, you require different treatment. In this example, this is different kidney stones taken out from the patient and buried into potatoes, boiled potatoes, and then use dual energy to scan them, try to classify them. As you can see that uric acid and all the rest of the kidney stones are well classified with a dual energy approach. Now I'm going to talk about a little bit recent study or research done on the dual energy, which is a dual energy cardiac. Because the fast KV switching method, the beams are switched at a fraction of a millisecond, so it's very tolerable to any motion because in a fraction of a millisecond, the object has not moved very much. So this is a phantom study carried out together with the Mayo Clinic, where they have a cardiac phantom where the heart is a pretty realistic phantom that can pump at any heart rate as we desire. As you can see here, with fast KV switching, you can freeze the heart motion. Also, you can separate different materials, as shown in this graph. Another potential application is for dual energy scout. Previously, up to now, for CT, scout is only used for landmark purposes. You're basically saying where do I want to start scan, where do I end the scan. However, with the dual energy fast KV switching, you can generate scout-based dual energy sinograms or projections, as illustrated over here. Here is a conventional scout where all the structures are overlapped. And with the dual energy fast KV switching scout, you can remove the bones and then only leave the soft tissues and look at some diseases and so forth. So scout is no longer a simple landmark tool. It can have the potential to do diagnosis. So in summary, Gemstone spectral imaging, which is a fast KV switching methodology, provide an advanced platform to enable CT to move beyond an anatomical modality. And it provides useful information, additional information to help to characterize tumors and to differentiate different materials or different soft tissues. It also has a capability to reduce image artifact. And if you look at current GSI's research, the active research area are in the cardiac imaging, where you want to separate calcium and iodine. You want to do different plaque characterizations. Also in the super low dose spectral projection imaging, where you want to move the scout beyond the anatomical landmark. Thank you very much.